Como dice Marie Curie, en la vida no existe nada que temer, solo cosas que comprender. Recuerden correr y buscar la manera de aprender que más le divierta. Neil deGrasse Tyson dice: nadie que es curioso es tonto. Las personas que no hacen preguntas permanecen ignorantes el resto de su vida. Y para ustedes, esto es curiosidad científica. Corillo, buenas, ¿cómo están todos? Antes de empezar el capítulo, quiero que sepan que tienen que ir a jaboneradongato.com, porque los jabones de Jabonera Don Gato son hechos a mano con ingredientes naturales y seguros para la piel, además que huelen súper ricos, así que no se pierdan la oportunidad, especialmente porque ahora pueden ir a jaboneradongato.com y cuando vayas a pagar, pones el código Curiosidad Científica Podcast para 10% de descuento. Vamos al capítulo. Welcome everybody to Curiosidad Científica Podcast, and you're gonna say, why are you speaking English, Agustin? And it's because I have my friend Daniel Whiteson with me. He's a particle physicist, the top podcaster of the Daniel and Jorge Explain the Universe. And I know because I listened to most of your episodes, including the latest one, about how you guys create the podcast and everything else, and that's super cool that I know that thousands of people from all over the planet are writing to you guys. That's really exciting. Not just that, you guys are authors of the first book. It was We Have No Idea, A Guide to the Unknown Universe, and your latest book that actually I have in here too, because the first one I loan to somebody and I haven't get it back yet, but at least the latest one, go and get it. Pretty much frequently asked questions about the universe. That's the latest book. And Daniel, welcome back. You have somebody that is a paleobiologist that is beating you in the amount of times that you've been in the podcast. He have like one more than you, I think. This is your third time.
All right. Well, thank you very much for having me. And now I see how you motivate your guests to come back, because we all want to be number one in the rankings.
Yeah.
So you have to invite me again.
Yeah, you will be. Believe me, I always have a lot of doubts and questions, especially in the field that you're covering. Is particle physics. How do you study something that you cannot really see? Or can we see particles?
Yeah, that's a great question. What is it that we're actually seeing? In the end, physics, we talk a lot about the theory, but the goal of it is to explain what we see, is to explain our experience and our experiments. And so you're right that we should focus on what it is we're actually seeing. When I teach modern physics and the beginning of quantum mechanics, I always start with the experiments. What did we see that motivated us to come up with these crazy ideas about how we think things work? And so we can talk about things like the photoelectric effect, where you see individual electrons boiled off of metal, or black body radiation, where you're measuring photons coming off of things, or of course the double slit experiment, where you see particles interfering with themselves. And so, while you can take like pictures of atoms, whether or not you're actually seeing a particle is confusing, because it makes you think about like, what is it that I'm seeing? What is actually there? And I think a lot of people imagine a particle is like a tiny bit of stuff flying through space, but it's really something much, much weirder. And if you ask like 10 particle physicists, what is a particle, you'll get 10 different answers. And so in some sense, it's still kind of philosophical. What it is we're talking about, what our picture of the universe is in our minds is different from person to person.
Wow, that's super awesome. So before we get to the bigger questions, I want to ask you a question that I hear you always ask your the people you interview that usually write novels, and it's in the transporter in Star Trek? You know what I'm going to ask you, right?
I ask people this question about whether transporters kill you and clone you or actually transport you, because I don't know what the answer is. It comes down to, what does it mean to be you? If what it means to be me is just the organization of a bunch of bits, not the bits themselves, then, tearing me apart and making me somewhere else is transporting me, because it creates me over there. On the other hand, if there's something about these particles that actually make me up right now that defines me, then it's not me on the other side of the transporter. It's a copy of me. It's not the Daniel who was originally in the world. And so I don't know. And the scary thing is that we're not that far from being able to build one. I mean, we can do quantum teleportation. We can take quantum systems apart and we can recreate them across space, not instantaneously, but across space using light beams and all sorts of information transfer. And so we can sort of copy quantum systems. We're pretty far from being able to copy a quantum system as big as me or as big as you, but that's a technical problem. That's like for the engineers. We've done the physics. The physics is solid. So one day we might actually have these devices and actually be confronted with these questions of like, the president goes in on one side. Is it the president on the other side, or is it somebody else? Right. So I don't know the answer. And what amazes me when I ask all these novelists is nobody ever says, I don't know. They always have an opinion. They always think it's one or the other. Surprised that nobody else punts on the question. So that's what I'm going to do. I'm going to punt. I'm going to say, I don't know, because that's the best answer. That's the best answer in philosophy.
Yeah, and if we know about particles, some particles, like electrons can be here and suddenly they just don't want to be here and appear somewhere else. So how do I know I'm going to be 100% me when you divide my particles apart and then an electron say like, you know what? I'm going to be in a superposition somewhere else. I don't know.
That's right. Yeah, exactly.
All right. Man, I want to talk about the Nobel Prize last year. It was about particle entanglement. And it is a little kind of difficult thing to imagine because we always see the universe kind of in a, like a bigger thing and kind of Newtonian stuff. And it's kind of hard, even if you understand physics about, the speed of the universe, like the speed of light and kind of some rules that is a law that nothing can go above that. But before I go a little over that, what is an entanglement in physics?
Yeah, great question. You hear this all the time. Particles are entangled. What it really means is that particles have something about their fate in common. And I think the best way to think about it is to think about it in terms of having a single wave function that describes two particles, instead of having two particles as separate objects. Now they're really connected. They're like part of the same thing. And, to give a specific example, say you have a photon and it decays to an electron and a positron. So an electron and its antiparticle. If the photon had no overall spin and the electron has spin up, then the positron has to have spin down, right? So these two particles are linked because they come from the same photon. So a single photon, because of conservation of momentum, its decay particles have to have the same momentum, and that includes spin. So if the electron has spin up, the proton has to have spin down. So these two things are linked. And that's a very classical picture, right? There's no quantum mechanical fuzziness so far. This is just conservation of momentum. But what happens if those particles are uncertain? Like what if you have a photon produce an electron and produce a positron, and you don't know whether the electron is spin up or down? So now the electron might be spin up and it might be spin down. But conservation of momentum still holds. If the electron is spin up, then the positron has to be spin down. And if the electron is spin down, the positron has to be spin up. So now these two particles are entangled, meaning that what happens to the electron is connected to what happens to the positron. They have to be the opposite, even if their combined fate is uncertain. And so instead of thinking about it like, oh, there's some quantum mechanical probability for one particle and there's a quantum mechanical probability for the other, now you have to think about them as a pair. You say there's a quantum mechanical probability for electron to be spin up and positron to be spin down, And there's a probability for the electron to be spin down and the positron to be spin up. They're entangled. You can't separate them and say we're going to treat them as different objects. There's really a single wave function that covers both particles now.
Oh, so pretty much it's just one system. So,
Yeah,
but in our minds, we want to separate, like, no. If this is an electron, this is a positron, there are different particles. But pretty much it's like, no, this is one system. It's a whole system with different, points or areas in the system. Okay, so how do
exactly. And separating things is a very powerful trick. We use it in physics all the time. Like if I want to understand the solar system, I say, well, I'm going to ignore all the other stars out there, and I'm going to ignore all the other galaxies, because including the whole universe in every calculation is a nightmare. So usually you can make the approximation and you can ignore most of the universe when you calculate about one specific thing. So that's really important trick we use all the time. But sometimes you can't, right? When you calculate what happens to the Earth, you can't ignore the sun. It's a big deal. And so in this one example, you want to treat it, you're tempted to treat an electron like a single particle, but really, as you say, it's part of a combined system that treats the two together. They are very closely linked, so you can't cut them in half and treat them independently.
Okay, so pretty much the answer is that they both have the same wave function, if you want to say it that way.
Yes.
So when it collapses, the function, it collapses for both particles because they're in one system.
Exactly.
Okay, all right. And how do we test this? How it happened? Because people won Nobel prizes for testing these things. How do we got that conclusion?
Yeah, it's really tricky. It requires some really clever experiments, because initially it seems like it might be impossible to test. One question that we wonder about in these systems is if these probabilities are real. We don't know the answer to whether the electron is spin up or down. Does that mean that there is no answer, or just that we do not know it? This is a deep question in the philosophy of quantum mechanics. And people were wondering, like, is this probability, is this uncertainty a reflection of our lack of knowledge? Or is it a reflection of the lack of the existence of that information? There's lots of things that I don't know. For example, you might say, what is the mass of the Earth? Well, it has a specific mass. Like, there is a number, a perfect number that describes the mass of the Earth. I measure it using imperfect devices, and I get a number with uncertainty on it. So that uncertainty reflects my lack of knowledge. But there is a true answer out there in some philosophical sense. But people were wondering, like, in the case of the electrons, do they already know which one is spin up and which one is spin down? And then when we measure it, they tell us? Or is the act of measuring it actually force the universe to pick one or the other? That was the deep question people were asking about this, because that's pretty weird, right? We're used to thinking about the universe as operating like a machine, and we observe it. The idea that the universe maintains uncertainty, that the universe doesn't make a decision until we ask the question, that's a very different universe than the one a lot of people imagine they lived in. And the trouble is, coming up with an experiment to tell the difference is hard, because if you just measure the electron, you get a spin up or a spin down. How can you tell if it was unknown before you asked or known before you asked? How could you possibly tell the difference, right? And so for a long time, people thought, well, it's impossible to tell. It's just a philosophical question. You could never determine it. But then there was a clever dude named John Bell, and he came up with a really clever experiment, but it's subtle, right? And it's not a smoking gun experiment. It's not like you do one experiment and you look at the answer and you can tell, okay, obviously the electron knew it all along, whether it was spin up or spin down, or no, obviously it didn't know. It's a subtle experiment because you have to run the experiment like 1,000 times. And it's in the patterns of the experiment, the probabilities, the statistics that comes out of it, that you can tell the difference. And so the way the experiment goes is you have your electron and your positron, and you measure both of them. But you don't just measure their spin in one direction. You can measure their spin in lots of directions. Like, if one electron is spin up and the other one is spin down, and you measure the spin along that axis, you'll get up and down. But if you flip it around, you'll get down and up. Cool, that's pretty straightforward. What happens if you, instead of measuring along the axis where they have up and down, you tilt your apparatus by like 90 degrees? So, the electron is spin up or down, but you're measuring it kind of sideways. Well, then each one has to decide, are you up or are you down? And in a sense of classical spin, like if you're thinking about a beach ball that's actually rotating, right? It's rotating around one axis. That's a very different picture from the way spin exists for electrons. In a classical picture, as you tilt and measure the spin, along the axis where it's not spinning, you'll continuously get a smaller and smaller value, and then you'll get zero. But the electron is either spin up or spin down along any axis. It's not a continuous set, it's quantized.
Mm-hmm.
So you pick any axis and ask the electron, are you spin up or down? It'll tell you, oh, I'm up, oh, I'm down, oh, I'm up, oh, I'm down. And so you can ask along any axis, and the probability changes as you change that angle. So the Bell experiment says, pick a bunch of axes in advance at random. So one up, one left, one right, whatever. Pick 3 random angles in advance, and then do your experiment and measure the electron and the positron spins. And based on the relative angles, you should get some correlations. Like if the angles are all the same, you should always get, the same answer. If the angles are large, then you'll get potentially different answers. And the cool thing about Bell's calculations is that he predicts that if the answer is not determined in advance, you'll get a different pattern of answers than if the answer is determined in advance. And it comes out of how this information is propagated, how the quantum mechanics maintains this superposition. It takes advantage of the interference effects between these probabilities to change the chances that you're going to get more ups or downs in various scenarios. That's probably as far as we can go without actually looking at the mathematics of Bell's inequality.
Nice. So pretty much that goes to the point of the EPR paradox, right? That Einstein, Podolsky, and Rosen, they say like the universe is it cannot be random, and then they were kind of arguing with Niels Bohr, if I'm correct, and what he was trying to propose is that actually the particles and all the system already have an answer. We just don't know the answer. So how the Bell or what was the answer when Bell looked into it? It was actually like, oh yeah, we even tilt the axis and all that, and we have this result, and the result says, oh yeah, this is random. We will never know if the ball was blue or red. It happened.
Yeah, so Einstein and his collaborators came up with this great thought experiment because they thought this was outrageous. Like, it's ridiculous to imagine that it's not determined until you measure, and here's proof. So they came up with what they thought was a ridiculous scenario that demonstrated that it was nonsense. And they said, what if the electron and positron are far apart? Like, you created this and we talked about their connections and the probabilities, but what if they're really distant in space? Like, create them and then don't touch them and let them drift apart so they're like a light year apart or something. Then how could it be possible that when you measure the electron that somehow it collapses the wave function of the positron? If they are really not determined in advance, then somehow the positron has to hear about the fact that the electron was measured so that it knows to collapse its wave function, but that violates relativity, it seems. It seems like that's instantaneous action at a distance. And we know in the universe, you can't send any information faster than the speed of light. There's this cone around you, we call a light cone. Your actions can only propagate out at the speed of light with information. And so they can't affect anything outside of this distance, which grows with time. And we call it a light cone because we imagine it in 2 dimensions, but really in 3D, it's like a growing sphere. And so Einstein was like, obviously, this is nonsense because it predicts that these particles would be communicating somehow faster than the speed of light. And so then people did these experiments. They're like, well, let's check. And so they did Bell's experiments, and they did them at greater and greater distances. And at first, it's hard to prepare these particles and to have them be isolated so they don't get messed up by other stuff. They preserve their original quantum state, and then to measure them. And now they've done these experiments like over thousands of miles so that we're very, very sure there's no way the 2 particles can communicate. There's no like loophole or, trick or anything that tells you that these particles can be communicating somehow. We're very certain that the collapse is happening instantaneously across space and time. And that's bonkers, right? That's
It
like,
is pretty
but it's
crazy.
also awesome because it means
It
that we
is pretty
live in a
awesome too,
weird
yeah.
universe. And who wants to live in a boring universe, right? We want to live in a crazy universe. And a lot of people think, oh, well, that means relativity is wrong, or that means that you can send information faster than the speed of light. And none of those things are true, right? Those two things are not true. They sound like they're true, but they're not. And there's some really crucial nuances in understanding how that works.
Okay, yeah. That was two questions that I have, like the speed of light and that, how does information travel. So you already hit that. So well, you kind of say that already, because my other question was that does entanglement break the laws of physics? Do you think, like, because we already established at the beginning that it's just one system. So that means like the system can propagate for light years, right? So, wow, that's kind of crazy, what I'm thinking right now.
Well, what it tells you is that quantum mechanics is non-local, meaning you can have a quantum system that's extended over space and time, and if it collapses anywhere, it collapses everywhere. So collapses simultaneously, even if it's really, really big, right? We're thinking about quantum mechanics typically as like, oh, tiny particles, tiny little things.
Yeah,
But if you
points.
create these entangled particles and let them drift apart, you have a big quantum system, right? One that can be like light years apart in principle. And so we have to think about how that happens. And the way to think about it is not like the electron does something and sends a message to the positron. That's not what happens. What happens is it's a single system, as we talked about before. The whole thing just collapses. It's like a balloon. I mean, actually, that's not true, because a balloon, you pop it one place, it doesn't immediately pop elsewhere. But, you know, it's something that if you touch it, it instantly collapses everywhere across space and time. And that doesn't actually send any information. Like, it doesn't violate relativity because there's no information actually sent. It's not like the electron and positron are talking to each other. It's one thing that collapses. And you can convince yourself of this because there's no way to use this to send information. Like if you and I were on opposite sides of the universe and we had two entangled particles, could we somehow come up with a clever way to talk to each other? Could I influence your particle using my particle to send you, you know, a series of ones and zeros or bleeps and blips or something? And people are always writing me saying, like, if they collapse at the same time, then here's my design for a quantum information device. And they're very clever, and the design is always the same. And it's like this: I measure my particle, and that collapses your particle, and you notice that. And then you can tell that your particle's collapsed, and therefore I've sent you information. And the flaw is that you can't notice that. Like if I measure my particle, yes, it collapses the wave function, but you have no way of knowing that your particle's wave function is collapsed. You can't look at it and say, is it collapsed or not? All you can do is look at it and say, is it spin up or spin down? Now, if it's collapsed, then that answer is determined. If it's not collapsed, the answer is not yet determined. But you don't have any way of knowing. And that's the loophole with Bell's experiments. There's no single experiment you can do to prove whether the information was determined. It's this statistical pattern that emerges that tells you that over a big ensemble, they weren't yet determined. So you can't use quantum entangled particles to communicate faster than the speed of light. Unfortunately, that would be awesome. And so it doesn't violate relativity. It's weird because on one hand, it does collapse instantaneously over space-time, which seems like it should violate relativity. But relativity doesn't say you can't have non-local things. It says you can't send information faster than the speed of light. And that's the rub.
Yeah, I would say like viable information, because like you said, that even if you look or I decide to look and I'm in another universe and you're sending me information and I just look, then I was gonna be the one who collapsed that particle. So I would not know if you look at it before me. It's kind of like the Schrodinger again. You know, like the cat and Schrodinger, it could be alive or dead, but until I look, I would not know anything until I take a look. That's so great. Well, you have this, like I sent you my print because you answer a lot of questions that I have here just recurrently. So that's great. That's great.
You know, there's a related question which comes up kind of often on the podcast, which is about black holes. Like, instead of having two quantum particles that are really far apart and wondering what happens when you measure one, do you collapse the other? What if you let one of them go inside a black hole, right? And then you can imagine, ooh, what if there's a physicist inside the black hole? They get one of the quantum entangled particles and they measure it. Does it still collapse the wave function of the other one, right? Because in
No
the previous
information.
example, we were talking about sending information faster than light. Now we're talking about sending information out of a black hole, which, like,
That
man, doesn't
anything
that
is
break?
supposed to come out, right?
Right, right. So the first example seems like it breaks special relativity because it sends information faster than the speed of light. The second one seems like it breaks general relativity because it sends information outside of a black hole, but the answer is the same. It doesn't. And that's because, well, number one, we don't know actually what happens if you do this experiment, because now we're mixing quantum mechanics and gravity, and we don't know how to do that. Like, we have no theory of quantum gravity. We can do quantum mechanics in flat space, and we can do quantum mechanics in slightly curved space, but we don't know what happens when you have quantum particles and very strong gravity. Like, we just don't know. You know, for example, if you have two quantum particles and their position is uncertain, what is their gravity? Is their gravity uncertain? Does
Mm-hmm.
gravity somehow collapse their wave function? We don't know. But here's a guess as to what happens with a particle in the black hole, not knowing the theory of quantum gravity, is that it does collapse the wave function for the person inside the black hole. And because the quantum mechanical wave function is extended, it's a single wave function for both particles, it also collapses the one outside the black hole. But like in the previous example, that doesn't send information. There's no way for the experimenter
Yeah.
inside the black hole to use that to say, here's what it's like inside a black hole, or send me a pizza, please, and ask for specific
Mm-hmm.
toppings. There's no way to use that to send information. So I think that it does collapse it across the event horizon, but it doesn't transmit any information, so it doesn't break general relativity.
Wow, that's a really good idea to think about. And then with what you said, then I thought about um, maybe that connection
Mm-hmm.
will still be there, because isn't it like the wave function, isn't it kind of like a field? You know, like they're kind of in a field that is entangled together. And
Mm-hmm.
we know about particles and kind of like matter, and the
Mm-hmm.
black hole just it kind of matter, but fields does, you know, like that gravity have any effects in the fields, you know, in
Yeah,
quantum fields?
it's a great question. The way we've been talking about it so far, we think about individual particles and their wave function. That's sort of an old-fashioned way to think about quantum mechanics. In around the 1950s, that whole way of thinking was replaced with a view of particles as part of fields. So instead of having individual particles, each with a wave function that determines what happens, instead you have a quantum field that can describe many particles at once. People were having trouble, like, how do I calculate what happens when a particle disappears or more particles appear? And the individual particle calculation made that really a mess. So instead of like thinking about individual drops in the ocean, people were like, let's just think about the whole wave together, man. That's much more sensible. So now we think about particles as ripples in fields, but the answers don't really change. Like, all the things we talked about in terms of particles and their wave functions also apply to quantum fields. So instead of thinking about a wave function, just think about a ripple in the quantum field. So yes, black holes can affect quantum fields, and all of these quantum properties that we talked about also apply to fields. And the electron and the positron are actually two different ripples in the electron field. It's not like the positron has its own field. The electron and the positron are two different ways that a single field can wiggle.
Okay, okay. Wow, this is so awesome. This is so it, I now that I do understand a lot more about particle physics, it makes so much sense. I don't know if everybody that is listening to this already say like, oh God, this is too hard. But it makes a lot of sense. It makes a lot of sense. For some reason, it makes sense. Since
It's
you talk
incredible
about
to me that we can spend all this time, observing the universe and come up with this crazy picture of what's going on at the tiny level. Like, you can't see any of this stuff, but unless you do special experiments to reveal some of it. But we can do these crazy calculations, and it mostly works. And it works really, really well. Like, the calculations we do agree with the experiments we make to, like, many decimal places. So it almost gives you the feeling like this isn't just a way of describing the universe, maybe we're revealing like what's actually going on. We've like found the source code of the universe or something.
Wow, that's super awesome. Super awesome. One thing that I think I haven't catch up with you since I think probably the first or second conversation about particles. When you have a particles, pretty much they go in pairs. You have the electron and the positron and this and that. And even Hawking talk about a black hole losing mass because of that. It's because one of them will escape and the other one will stay. But when we talk then about dark matter, that I know you are studying dark matter, or at least you were in that field. Are you still in that field?
Yeah, I'm still looking for dark matter. Still haven't found it.
Can you explain to us a little bit about using the collider, the particle collider? How can we do that? Because it's kind of like the same idea of the couple particles going to the to the black hole. The difference is like you're trying to see a particle that might not be there.
Yeah, great. So in the case of Hawking radiation, remember a couple of things. One is that this is a theory. So we've never seen Hawking radiation. We don't know that it happens, though it's pretty well supported. And the other is that Hawking radiation is an argument about what happens as black holes get hotter or colder. Essentially, what happens to quantum fields near an event horizon. There's a lot of descriptions about particles and antiparticles near an event horizon, and one falls in and one doesn't. None of those are realistic. Those are like little cartoon, hand wavy doodles to maybe give you a picture. But the truth is, because we don't know how gravity works for particles, we don't have a microphysical picture. We have only this higher level picture. It's sort of like saying we understand how gases work, but we haven't yet figured out atoms. We're sort of at that level for Hawking radiation. And there's stories, and you hear them all the time, but I think a lot of them are misleading. So it's important to remember that for Hawking radiation, we only have sort of the bigger picture idea of what might be happening. The microphysics of it depends on quantum gravity that we don't know. There's a lot of misleading stuff out there, including by Hawking. I read his book, and he tells these stories, and I'm like, you don't know that. And later he admits, yeah, I know that was just sort of a story.
This one.
Yeah, exactly.
I know that was a little, I don't know, that's a little bit of a stretch.
Yeah, right. And I mean, I don't mean to be like egotistical and criticize Hawking. The man is smarter than I am, but he admits himself that those stories are fuzzy. But to your question about dark matter, we don't know what dark matter is. And we think maybe dark matter is a particle. Why? Because everything else is a particle. And so that's the only thing we know how to do, right? It's sort of like if you're a bird researcher and all you know how to do is look for birds in the forest, so you go look for birds. So we're hoping dark matter is a particle, but we could be wrong. It could be something totally different.
It could be a bird that we can see.
It could be a bird, exactly. Or it could be a mouse, right? Or it could be a leopard. And in the collider, it might be that when you smash two protons together, which is what we do, that sometimes dark matter is created. And that if dark matter has some way of interacting with our matter, like it bumps against it or it can exchange momentum somehow, and we don't know if that's true. So this is assumption number two. Assumption number one is dark matter is a particle. Assumption number two is it has some connection to our kind of matter. Then occasionally when you smash protons together, you should make some dark matter. Problem is, dark matter is invisible. Like it doesn't give off any light, doesn't reflect light. We don't think it interacts very often with our matter. So if you did make some, it would just fly out of your collider invisibly, just like neutrinos. Neutrinos are a particle we know and love, and we're certain they exist, but they almost never interact with our colliders. We can't see them. We make them all the time in colliders, and they're invisible. So what we have to do if we're going to find dark matter at a collider is figure out a way to see an invisible particle. And that sounds kind of impossible, but we can do it with a trick. The trick is to use conservation of momentum. And we know when the particles collide, they're colliding along a line. And so if we add up the momentum of all the particles perpendicular to that line, then we know that it should add up to zero. because the initial momentum along that line was zero. You have the beam line, the particles come in, there's nothing moving sideways, basically. So you add up all the sideways momentum, sideways to the beam, it should all add back up to zero. Like if you have two cars that come in a collision and they bounce off each other and go sideways, then their momentum opposite is zero if you add it all up. And so what we do is we do these collisions, and then we add up the momentum of everything that flew out sideways, and we look to see if it doesn't add up to zero. We look to see, oh, maybe there was something missing. Because imagine, for example, you had a car and it bounced against an invisible dark matter car and got pushed sideways. You'd be like, well, that was weird, right? All of a sudden, this car momentum changed and I didn't notice anything. So if in this collision, all of a sudden there's a bunch of particles spraying out in one direction and nothing on the other side, then we're like, there must have been something invisible on that side, something we didn't see, but we can tell it was there because we can see something pushing against it, like the car bouncing against a dark matter car. And so that's what we're looking for, is we're looking for an imbalance in momentum of the particles that come out of the collision to tell us there must be something invisible to balance the momentum. And that's sort of similar to how the neutrino was discovered initially. People were looking at radioactive decay and they noticed, hey, the momentum doesn't add up. So Pauli was like, well, there must be a little neutral particle flying away with that momentum. And that's what neutrino means in Italian, right? Little neutral particle. And so like that, we're looking for some invisible particle carrying away momentum that we think may not be a neutrino. We haven't found anything yet. I mean, that happens at the collider. We see that all the time, but we can explain everything we've seen using neutrinos and other invisible particles we know. We're looking for invisible particles we don't know, and we haven't seen any yet, but we're still looking.
Wow, that's pretty impressive, because what you said about maintaining the momentum, and pretty much, if I can say it in my way, it's like if I hit my fist, but suddenly I have 10 fingers, and suddenly when I look back to put all my fists back together, it's like, oh, where's my thumb? I'm missing one thumb. Well, I have these 5 fingers, but the other one's not. But that's the thing, that those are the questions that breaks my mind, because even though you can add up, like, okay, we know there's neutrinos, so what we're missing that our sensors are not catching, that mass or that missing part, it looks like a neutrino. But how do we know? Well, I know probably we don't know, but the hard question is, what if the dark matter particle have the same, and I'm doing quotes in it, what it does have like the same mass of the neutrino? We would not know. So what if they have the same characteristics, but actually doesn't like get together with the electromagnetic? You would not know, because you would thought it is a neutrino and it could be a dark matter particle.
Yeah, that would be very tricky if dark matter happened to have the same mass as neutrinos. That would make it harder to find. We still might be able to find it, because with neutrinos, not only do we know their mass or close to what their mass might be, but we also can predict very precisely how often they are made at the colliders. And so if we see additional missing energy events, like if we see a bunch of these weird events more than we expect, then we could say, well, there must be something else. If they look just like the neutrino events, but there's more of them, it'll be very tricky to figure out what that is. But if there's an excess of events and frequency of this happening, then we'll know it. And so that's something we look for. So when we look for, we look for not only just a bunch of weird a bunch of weird events with an imbalance, we also look for an extra frequency of them. Like, are they happening more often than predicted?
Oh, wow. Man, you guys think about everything. Gosh. This is so beautiful, but it's so hard. It's so hard at the same time, because to me, every time you explain things, especially in your podcast, because I listen to you guys a lot too, because when I have doubts about what I'm explaining, I'm like, all right, let me go to my friends in there and try to understand. But that's the thing, like, sometimes I feel like you guys have been so far, and still there is so much we don't know. It is crazy. It's awesome, but it's kind of crazy. I don't know, I guess.
It is amazing how much we do know and how much we don't know. And it's exciting that we live in a moment where we know that we don't know very much. We know that most of the universe is made of dark matter and dark energy and all sorts of crazy stuff. We know that there are other deep rules about the universe that tell us how gravity works with quantum mechanics and quantum particles that we don't know yet. And so I wonder sometimes about physicists in 100 years looking back at us and like, would they think we were totally primitive and had basic misunderstanding about everything? Or would they be like, yeah, those guys knew what they were doing? I really wonder about that. I wish I could live for 500 years so I could see just like the evolution of these ideas, It'd be incredible, like explain some of this stuff to Isaac Newton or to Galileo, or blow their minds, It's incredible what we've achieved over the centuries.
Yeah, I was talking with a friend the other day, and they asked me, if you could travel in time, where do you go? And all of them were saying like, well, I would go to like whatever 900s, and I would like to see the Vikings. I would like to see the Rome how it was, and I always say, well, I want to be like 1,000 years from now to see where we are. And they're like, oh, you want to go to the future? Of course I want to go to the future. I would love, I'm dreaming about literally just Rick and Marty, have my gun and I just open a hole in the wall and go to whatever, to eat bagels in 1 second. I don't know.
Well, the good news is the future is time travel that you can actually do, right? We're going into the future right now. We're all sliding into the future. There's nothing we can do to prevent it. So as long as you live long enough, you could freeze your brain and come back in 500 years. You could never come back to today, of course, but you could actually see the future. That's exciting. Yeah.
That's pretty exciting.
I mean, I would go back like 30 years and buy stock in Apple,
and
then come back to the present. And then I'd be a zillionaire. I could found my own research university to research basic physics, to help all of humanity. That's what I would do with the time machine.
Wow, philanthropy. That's great. Kind of.
Yeah. Kind of.
I have one more question, since we talk about a little bit about black holes. I know that we have particles for most of the things, but still gravity, we don't really have a particle, and we don't have a good theory, especially in singularity. And the other day I was reading about the Planck length, and I think Brian Greene, I have his book around there. Brian Greene explained a little bit about like the Planck length. It's not literally like the point where it's like I don't want to say something that is wrong, but he kind of tried to say that that singularity point is not necessarily that is like something that is like the infinite mass or infinite gravity or infinite whatever. It's more that we don't have a good mathematical explanation up to that scale. What would you say about that scale? What is the Planck length, and what's the problem that we cannot explain gravity by any means? Not the Newton, not the Einstein, no relativity, or no quantum. What's going on with that?
Yeah, great question. The issue is that general relativity makes some predictions, and some of those predictions seem crazy. And one of them is that inside a black hole, there's this runaway effect. Things get denser, so gravity gets stronger. So things get denser, so gravity gets stronger, ... forever, until you have a point that has infinite density. And that's what general relativity predicts. And the question is, what do you do with that prediction? And most people don't take that prediction seriously. They don't think, oh, well, that means singularities are real and they're out there in the universe. What they take it to mean is that the theory is broken, that the theory only works in some scenarios. And that's not unusual. Every theory is like that. Take your theory of fluid dynamics. It works for water in some temperature ranges. When water gets too hot, it turns into gas. Your theory of fluid dynamics doesn't work anymore. It's a different phase. Water gets too cold, your theory doesn't work anymore because now it's a solid. So every theory, so every theory describes a certain phase of physics. And that's true also for general relativity, we think. And what happens when things get really, really small and gravity is really, really strong, nobody knows. We know that quantum mechanics says you can't have a singularity, that would violate the uncertainty principle. because you'd have a point, you'd know a lot about its mass, and you know a lot about its location. Just can't happen. There's like a minimum fuzziness to the universe according to quantum mechanics. So people say, well, that means that relativity breaks down at some point. When does relativity break down? At what point can we not trust it anymore? We don't know the answer to that question, but we can estimate it, right? We can say, well, maybe there's a minimum size to the universe. Maybe. How could we possibly estimate it? And so we don't know. We need a theory of quantum gravity. But people like to, when you don't know how to answer a question, they like to make approximations. They like to make estimates. Like if you said, well, how many piano tuners are there in New York City? I don't know, but, maybe we could estimate it using a few fuzzy arguments about the number of people and how often a piano needs tuning and blah, 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 blah. So can we do that with this? Can we figure out when relativity breaks down? What is the smallest scale to the universe? We don't know the answer. And we have one way to estimate it, which is like take all the fundamental constants, look at their units. We have speed of light. We have the gravitational constant. We have Planck's constant. Can we somehow mash those together so that we get something with the right units, right? And you can take H and C and G and mash them together and take square roots, and you get an answer with a distance. What does that distance mean? We don't know. It might be the scale at which relativity breaks down. It might be the tiniest distance that makes sense in the universe. But it might not. It might be off by a factor of 10 or a billion. It's like if I said, well, how much money does Augustine make in a year? I don't know. Well, let me estimate. Okay, here's a number that has dollars in it, and here's a number that has years in it. I'll just divide those two numbers, and that's my answer. How likely is that to be right? Yeah. Not at all likely to be right, but it's the best we can do. So it's simultaneously a terrible, very unreliable estimate. People widely describe it as the minimum distance scale of the universe. It's not that at all. It's just a terrible estimate of it. And it's also the best estimate we have, right? So that's why people talk about it, because it's the only estimate we have. So it's like a vague way to get a sense for maybe where the distance scale at which relativity breaks down and quantum mechanics takes over, and we need a new theory of quantum gravity. But it could be off by a factor of a zillion, and we wouldn't know.
Yeah, that's crazy, because when you read about it, it's just like, oh, yeah, that's around 10 to the negative 32, I think it is. And it's like, how do you guys come up with that number? Because
it's an estimate.
Even our detectors can see it smaller than what, like negative 10 to the negative 23 or negative 26, something like that. So how do we
10 to the
know?
negative 21 is about the smallest scale we've ever probed at particle colliders. So this is like a trillion times smaller.
That's my point. How do you come up with it?
Yeah, that's, it's like the ratio of the size of, a grain of sand to the solar system or something. It's like, it's a big extrapolation. So don't trust it. Just say it gives you a sense of maybe. And it's a good thing to do. Like if you don't know how to do a calculation, try the dumbest thing first. It's better than doing nothing. It's better than doing nothing. Right? Make an estimate, then improve it, criticize it. Just don't make an estimate and then trust it.
Yeah.
Remember that it's an estimate. It's the first step. And then in 50 years, hopefully we'll laugh about that. Like the first estimates of pi, the Egyptians or whatever were like, pi is about 4. And then later it's like, oh, it's 22 over 7. And now we know pi to a zillion digits.
Oh, yeah.
It's good to have an estimate, and then it's good to improve it.
That's great. Daniel, I thought it was going to be more difficult, the entanglement thing, but it was kind of pretty simple. I don't know. Like, yeah, just one system is that's it. It wasn't nothing magical about it. Well, it's magical. It's physics. I love it.
You're thinking like a physicist, right? You got it all in your brain now. It's all intuitive to you, right?
Yeah, like you just said, even if you don't know, you have to start talking about it to maybe in the future somebody more smart than me in this case, we'll have a new description, but I start the conversation. So that's the point.
And we're all hopeful that the future has lots of really smart people in it to figure out these problems.
Yeah, that's what we're trying. That's why we're trying here. And that's why I really love your podcast. I listen to a few science podcasts, but it is like you and Jorge Chan, you guys are like, when I listen to it, it's like listening to friends just talking, like chatting and jokes and puns, and sometimes I just working and listen to it, and I'm laughing by myself, and I know people are looking at me like, this guy is kind of crazy because
well, I love talking about this stuff, and I want everybody to experience the joy of physics, of thinking like a physicist and understanding the universe. And it's always fun to talk to Jorge. He's an old friend, and so we have fun talking about this stuff. And he's great at asking questions to help us understand like what's tricky and what's not. So, I'm just grateful that I get to talk about science and get to have fun doing it, and that anybody's listening. So thanks very much for your kind words. I appreciate it.
Thanks, you. So you guys, you can find Daniel Whiteson in everything that he do, including his books. Like I said at the beginning, the frequently asked question about the universe. You can find that everywhere. And is this one too translated, like the first one, in all, even Spanish, Arabic, everything?
Yeah, lots of different languages.
That's great. Look at that. And your podcast, Daniel and Jorge Explain the Universe. So thank you, Daniel. I really, really appreciate your time. And let's see if you can beat my friend Jorge Velez. Actually, he's in California. He's the director of the California Natural History Museum. So he can take you to the real museum if you want. I can get you in contact with him.
That's a great museum. I love that museum. Yeah.
Well, I can literally send you his info if you want to take your kids with you to the actual museum where everything crazy is. You only in the actual museum, like up there, you see like 20-some% of what they actually have. What they actually have down there is crazy. So
this is the one in Los Angeles near USC, right? Oh,
yeah.
Wow.
Yeah.
I love that museum. I haven't been there forever.
That'd be great. I'm gonna then send you his phone, and I'm gonna let him know, because literally, if you want to see the actual museum, I'm pretty sure he can take you there. He's a really, really, really close friend. So
that's wonderful. Thank you.
All right, everybody. Just remember to find the way to learn that is the most entertaining for you. This is Agustin Valenzuela. You can find me. Do you guys have a social networks? Because I follow you on Instagram, but I barely see your posts. I don't know.
Yeah, we post more on Twitter and X right now. But yeah, we're Daniel and Jorge on everything.
Okay, nice. All right, everybody. See you until the next time.
Gracias y adiós.
Y para ustedes, esto es curiosidad científica.